Greetings, physicists. In this video, we're going to be discussing objects that oscillate back and forth with a regular period. So, we have a couple examples of this type of motion. One of them is to take a very smooth glass bowl and release some kind of spheroid object, some ball, like a golf ball or something. And we're going to pretend that it has very little friction. We're going to ignore that between it and the walls, and the ball is going to start rolling down the side. And at various points in the motion, it will be here, and then it will wind up back here, and then it's going to turn and go back. And it will go back and forth, and according to law of conservation of energy, if we don't lose any energy to friction, it will keep going from, some height h on the right side to some identical height h on the left, and then back to the right, and you can picture this going back and forth over and over. And when it gets to the edges, I know I drew a line here, but it's not actually at the very top of that motion. It would have an instantaneous velocity of 0, assuming it was released from 0. And then at the bottom, it would have used up all of its gravitational potential energy, and it would be going the fastest of the entire motion. So this is a repetitive motion. It would go one way, up to here, and then back, up to here, and then back and back and back. All right, you can picture this, I'm sure. And we're going to claim that that's similar to a couple of other types of motion. The first one we'll talk about is a pendulum. So if you had a ceiling, and you did the experiment where you pulled an object back, and this time it's just on a string, and you release it, and it's going to start to accelerate downward, and it's going to get to the bottom of the swing going really fast. And if you keep going, it's going to make it over here. And if we're analyzing this, right, the object has a difference in height, h, between here and like the bottom of the swing. We'll call that h. And then again, if there's no friction or air resistance or something, then it will reach that same height h on the other side of the swing, and then it will swing backwards. And so this motion hopefully is intuitively similar to the ball rolling inside of the glass bowl. We're going to make a connection between those two types of motion and another one, which is springs. Imagine you have a spring with a block hanging from it. All right, and we let it hang at its equilibrium position so that the forces are balanced. And then you're going to take your hand and you're going to stretch that spring all the way down to here. You stretch it by some height, h, from equilibrium. And then you release it. And you will release it from rest, so its initial speed will be 0 at this maximum stretch h. Sometimes we'll call this the amplitude. And then it will accelerate upward until it gets to this point, which is back at equilibrium. And at equilibrium, the forces will be balanced. So it's not going to stop there because it has some speed at this point. It has some v. And then, so it's going to keep going upward, and it's going to reach a point where it's all scrunched up. Let me see if I can draw that. And that's actually a point h above where you started. So if this was the original h, this is also h, but in the other direction. And that's where it will have used up all of its kinetic energy and turned it into gravitational potential. Well, not at this point. It will turn it into spring potential as well. And then from that point, it's going to stretch back. It's going to go back to equilibrium. And it's going to have a downward velocity. And if I drag this over, I'll have some room. And then it will go back down to here, back down to the original height h. And if we're not losing any energy, again, to friction or like air friction or which is drag, and the spring's not dissipating any energy, then this thing will just keep going back and forth. It will oscillate up and down. And you could also do this sideways. You could have a spring on a frictionless surface, and you could have it oscillate left and right if you were attaching it to a wall or something. And this would be the same sort of thing. And these motions are all similar. You can graph them, for instance. If you were to graph the position over time, here's time, here's position, of one of these, we start at some height h, right? All of them started at some height h. And then later, they came to an equilibrium position. And then they came to some height in the other direction, which we'll call negative h, right? With the pendulum, it was going left and right. So if right was positive, left was negative. Equilibrium would be straight vertical, that kind of thing. Same with the ball in the bowl. And with the spring, it was, if it's going left and right, you can do the same way. If you're going up and down, you can make one of those positive, one of those negative. And then sometime later, it would come back to equilibrium and then back to height h again, and it just keeps going back and forth as time goes on. But these are not straight lines on a position graph because the thing was accelerating, remember. There was a force causing this, the force of the spring or the force of gravity in the case of the hanging objects. And so what we get are curved lines. We get this kind of curve, and then this kind of curve. And if you're taken enough math, which by this point you should have, you should recognize this as a trig function. And it's a trig function that starts at the maximum amplitude and goes downward from there. So this is a cosine function. And we actually do have some things we can label for it. For instance, in a cosine function, the height of one of those peaks, we're going to call that the amplitude, and that corresponds here, if we go back up, to this height h. So this height h we can also call the amplitude. It was stretched from equilibrium by an amplitude a. That's what that means. If we were to time this from the point where it was stretched up to the other side and back to the original stretch, that would be, it started here and it ended at the same amplitude. We would say that's one full revolution, or we're going to call that a period. A period is the amount of time it takes from here to here. That's like a delta time, but we're going to use a capital T to denote period. And so, using that notation, I'm going to just kind of plug that into here. This function, this cosine function, this is position as a function of time. So I'll just make that a function, x as a function of time. What we find is that at 0, it has amplitude a, and then times the cosine of, well, it turns out this function will have a cosine of 2 pi t divided by the period. That is any function that has this general shape, this like oscillatory shape. We're going to call this a sinusoidal function. And they tend to look like variations of this formula. Okay, so at any time t, you could figure out what position this object had either been stretched from equilibrium by taking the amplitude being the max, right? Amplitude being this distance. So you could say A max if you want maximum amplitude. This position here would be like, if I'm here, I'm not obviously at maximum amplitude, I'm somewhere in between. So what we're finding when we calculate x is the amplitude at any given point along the curve. At any given time t, at time t here, we would have amplitude x here, where we take the maximum amplitude and multiply it by the cosine of 2 pi times whatever time we're at divided by the period. And the period is just a length of time, which if you're looking at this graph, a period would be from, you could say from here to here. That's a period. We got from one spot to the identical spot on the graph. Or it could be from here to here, right? Those are identical spots on the graph. It could be from this point to this point, because this is on the downward slope and this is on the downward slope, right? So that would be a period of time on the graph that would correspond to t. Keep that in mind. Now we're also going to have another variable that we're going to use to describe sinusoidal functions or oscillatory functions, which is that the period is typically measured in seconds, but it's the amount of seconds per one, I'll say one oscillation. It's a specific amount of time. And when we say seconds per oscillation, you don't usually include oscillation in the unit when you're like writing it. So if I ask in a test, what is the period of this pendulum back and forth, you would just give me it's 5 seconds, if that was the answer. You wouldn't say 5 seconds per oscillation. You could, but that's kind of implied in the term period. But we're also going to introduce a new term called frequency. And we'll use lowercase f for frequency. And the frequency is going to be defined as this. It's the number of oscillations that the object makes, the pendulum or the spring, in 1 second, exactly 1 second. And so I will define this, so frequency is going to be oscillations, mathematically speaking, oscillations per 1 second. Notice how these are similar. If a period is the number of seconds in one oscillation and the frequency is the number of oscillations in 1 second, by definition, those are inverses of each other. And just like I said with oscillations, if I said what was the period, or sorry, with period, what is the period of the pendulum? It was 5 seconds. Well, if I was asking frequency, right? I didn't say oscillations. If I say what is the frequency, we don't say. You could say oscillations per second. You could also say per seconds as a unit, where you don't include the word oscillation. Per seconds is the physics unit for frequency, and we're going to actually name that after a famous dead physicist. So a per second is the same as, so 1 per second is the same as 1 hertz. And they are, the two quantities are related like this. The frequency of an oscillating object is equal to 1 over its period. And you should be able to see that if I multiply by period and divide by frequency, I also get that the period is equal to 1 over the frequency. So those quantities are easy to interchange. Or at least I think they are. So going back to our equation we had that the position of an oscillatory, of an object that like the pendulum or the spring, was a cosine function. Specifically, it was the maximum amplitude times the cosine of 2 pi time divided by the period. Well, if period is on bottom of this function, we could also write this way. We could say that the position as a function of time could be graphed with a cosine, and I could just say 2 pi, and instead of 1 over t, I can just write frequency, because that's what this says. 1 over t is the same as frequency, and then I multiply by time. So both of those equations are equivalent for the position of a function, of an oscillatory function. And we'll call this type of motion, defined by this type of equation, as simple harmonic motion. Yeah, and what you might notice is that with the pendulum or the ball or the spring, if I displace the pendulum to the left, there is a force on the pendulum that pushes it back, essentially back to the right. If I displace the ball, again, these are the equilibrium positions, right? So if the ball is displaced, the delta x is to the left, then the force is actually going to push it back to the right. So the force and the displacement are always in opposite directions during simple harmonic motion. Same with the spring. If I just place the spring downward, that's the delta x, then the force goes upward. So that's another way to recognize simple harmonic motion if you didn't have the equations in front of you. Now let's look at a kinematic stack for this. Okay, we've got a position function like this. We have x and time, and we know it's a cosine function, so it starts out at 1, does one of these. What would a velocity function look like for this exact same motion? Well, the velocity is starting out at 0, right? The peaks here all have an instantaneous velocity, if you draw a tangent line there, of 0. So the velocity looks like it's going to start this way. And if you look at the slopes in the beginning of this position function, they're going downward until we get to here. And that's the steepest it gets is when it crosses the x-axis. So I'm going to get negative, and the most negative I get is going to be right there. And then I get over to this point, which the velocity again is 0. So at that point, the velocity is 0. Then I get to this point, and now we're going upwards, right? This is an upward trending slope, and it's at steepest when it crosses the x-axis. So right at that point, I should have a big velocity. And then I get up to here, and I'm back to 0 velocity. So you can kind of see where this is going. These two graphs are shifted from each other by, is it pi over 2 or something? Don't quote me on that, I'm bad at my trig. Okay, so we're going to get this function. Now you've got a trig function that starts at 0 and goes to max amplitude, so this is a sine function. But you're not used to seeing a sine function that starts out negative, so you're used to seeing it go up. So this is actually a negative sine function here. And if you go down, we could do the same thing and say, what's the acceleration? So let's do an acceleration graph with time. This slope here is as steep as it can get in the negative direction at the beginning. So the acceleration graph is going to start off down here. And then it goes to 0. At this point, the slope of this line is 0, and then it's positive, so we get positive here, 0 here, negative, 0, positive, 0, negative, 0, positive. And so the acceleration function would be one of these. So this one also looks like a cosine function, but we're starting at the negative 1, or the negative max amplitude instead of the positive. So this is a negative cosine function for the acceleration. And if you are in calculus, you will recognize that starting here with the cosine, the derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. So it follows what we had before in kinematics, where velocity is the derivative of position and acceleration is the derivative of cosine, or is the derivative of velocity. So don't, and if you're not in calculus, don't worry. That's just, you will get to that eventually. So if I want to then plot velocity as a function of time, if I want an equation for that specific function, I will get, remember it was a negative, right? So it was negative velocity, and we'll say maximum velocity. So this is like the velocity at the bottom of the trough, or at the bottom swing of the pendulum, the fastest it ever gets. And times the sine, because it was a negative sine function, of the same thing, 2 pi time divided by period. That's a capital T on bottom. But just like we did before, we can say that period on bottom is the same as frequency on top. So minus the maximum velocity times the sine of 2 pi frequency t. Now, I should point out that when I say velocity max, I'm talking about a speed at that point. Whether it's going left or right, the maximum speed has the same magnitude. So we're just plugging in speed there. And if you would like the acceleration as a function of time, we have this function, acceleration of time equal to the negative maximum acceleration times, and again it was a cosine, so it was a negative cosine function, and you guessed it, 2 pi t over capital T. Or if you want to do it in terms of frequency, that's negative a maximum cosine 2 pi ft. For me personally, I think that's easier to memorize, 2 pi ft. And then all you're doing at the front is whatever quantity you're measuring, it's that, the maximum of that quantity. And for acceleration, it's negative cosine, and for velocity, it's negative sine. And for position, right, up here for position, it's just a. A is still a position. It's x max, if you will. So this is all consistent. We just tend to call maximum position amplitude. So get used to that. We could also note some things, some similarities. When we are at maximum stretch, maximum position, we are at zero velocity. When we are at the equilibrium position, we are at maximum velocity, either positive or negative. When we are at maximum position, we are at maximum acceleration, but zero velocity. See how that goes? But when we are at maximum negative position, we are at maximum positive acceleration. So the displacement and the acceleration are in opposite directions because the force and the displacement are in opposite directions. So those are the similarities inherent in this. And we can make one more, let's do that. We can make one more acceleration equation. The acceleration, like I said, was based on the net force divided by mass, right? That's F equals ma. And that net force is actually a function of x, right? The farther this thing is moved from equilibrium, the greater the force it feels with the spring or with the pendulum, either way. And that will be equal to, for the spring specifically, minus k over m times x, because the force as a function of displacement for a spring is kx. There you go. So we're now going to talk about something that is similar to the objects going back and forth. It's a topic we've looked at before, which is circles. So we had uniform circular motion looked like this. We had an object that went around a circle like so at a constant linear velocity v. Now, if you look at a particle traveling around the circle, it has both a y-coordinate and an x-coordinate. We're going to consider the x-coordinate. So this is its radius, r, and this is the x distance here of that particle's position. And this is the angle through which it is rotated, this angle theta. And so if we look at that particle, you could define its x position as equal to, and let's further suppose that the radius here, that's the distance from the origin. We're gonna use the same term we used before, which is a. So instead of radius, I'm going to say the radius is equal to its amplitude. So we'll say it has an x position of a cosine theta. All right, and we also know that we can relate x and theta, right? We had this following equation. If it's going around in a circle at a constant linear speed, it also has a constant angular speed, and that angular speed was a delta theta over a delta time. If we're going to, let's solve this for theta. Theta essentially at any given time, if we start from zero angle and 0 seconds, we would get theta equal to omega t. Now, let's talk about this part of circles. If you go around a circle, your velocity is a 2 pi r, that's the distance you travel, divided by a period. That's the time you travel. Yeah? Well, a period is just going to be 1 over frequency. So I can also say that the velocity around the edge of the circle is a 2 pi r times a frequency. But we can also do this. V equals r omega for an object traveling at a constant angular velocity, right, around a circle. So V equals r times the rest of it is omega. So we could say V equals this 2 pi f times this r. And in our case, we called this r, we said that we're going to use the letter A for that. That's the amplitude. So that's V equal to 2 pi f times the amplitude. Or 2 pi f is going to be the same as omega, so it could also be omega times the amplitude. Now that is the linear velocity v. So when I'm going around this circle, that's the tangential velocity. If I'm thinking about it in terms of the x direction, then like when it's here, the tangential velocity is up, there is no x velocity at this point. There's some x and some y velocity at this point, and at the top, at the peak here, that velocity is all in the x direction. So this point here is the maximum x velocity that it will ever get. So we're going to say that this velocity equals 2 pi frequency times amplitude. That's really the maximum x direction velocity that we can possibly get. So I think we have one more thing to do here. I'm just going to go back up here to x equals a cosine theta, and I'm going to substitute in for theta omega t. And you'll see why. So x is going to be equal to a cosine. Instead of theta, I'm going to put omega t. But instead of omega, I'm going to put 2 pi f. So x equals a cosine 2 pi f t. Well, that's familiar. That equation is the same exact equation as a spring or a pendulum or a simple harmonic motion. So the equation for moving around a circle, at least for the x component of moving around the circle, is exactly the same as the equation for any other kind of simple harmonic motion. And so what we can say is if this is the maximum velocity in the x direction of a particle going around a circle, it is also going to be equal to the max velocity of a block on a spring oscillating back and forth, or a bob on a pendulum swinging back and forth. So this is a maximum velocity equation for any simple harmonic motion, and that will be useful to us. Now, one more circle thing I can do. We had a centripetal acceleration equation, was linear velocity squared divided by r. Well, I'm going to replace r with a because that's what we've been using this time. Okay, so let's do that thing we had before. That linear velocity was equal to 2 pi frequency a. So on top here, when I have linear velocity squared, that's 2 pi frequency a squared over a. Well, I'm going to lose one of the a's. on bottom, or on top, I'm going to lose one a, I'm going to lose the a on the bottom, and so what's left is the acceleration around a circle was 2 pi f, that part will be squared, and there will be 1a left over. All right? And again, it will follow the same thing, that this can work in simple harmonic motion as the maximum acceleration. This is an a max. It's maximum on the circle too, just at different points, right? So if we go up to this circle, we said that the velocity was maximum here at the top of the circle. In the x direction, it's maximum at the top of the circle. But at the top of the circle, the acceleration is centripetal. It's toward the center, which is in the y direction. So the maximum acceleration would actually be at one of the sides, right? Because here, the acceleration is toward the center of the circle. That's completely in the x direction. Now, the magnitude of the acceleration is the same everywhere, but everywhere else, it's not completely in the x direction. The only time it's maxed in the x direction is at the edges. All right? So we're going to say that that's our simple harmonic motion max equation. So what we're taking away from this are those two. The a max is 2 pi f squared times a, and the v max is 2 pi f a for all simple harmonic motion. And those will be the important things you're going to have to deal with for simple harmonic motion.